Hello, everybody, and welcome to the fifth episode of Honest Discussions. I'm your host, Dr. Brandon Patterson, and today we are going to be speaking with a fine young whippersnapper named Jake Matthews. Dr. Jake Matthews is from the Southwest Research Institute in San Antonio, Texas, and is a member of the research team studying the data coming from the JUNO satellite mission, which is dedicated to all things Jupiter. We're going to be discussing today how the sun interacts with Jupiter and magnetically connects with Jupiter through Kelvin-Helmholtz instabilities, which you're going to see are some pretty cool structures. We also get into what it's like to work on the JUNO mission and what it's like to be a physicist at the beginning of your career. It was an awesome conversation. I really enjoyed talking to Jake. And on that note, let's get to the show.
When I was a junior in high school, and that's when I took my first physics class, intro to physics class, and my teacher was different from other teachers that I've had in the past on just trying to make the what we did in class fun and the experiments fun, but also, of course, at the end where everyone still learns something. And he introduced me to physics, but also to the part of it that makes science interesting and important to society. So it stemmed from there, and I took a physics class ever since, every year after that. So,
What was his name? Let's give him a shout out.
Mr. Warner.
Yeah, shout out to Mr. Warner for making
That's
an earth
right.
scientist.
Yes, Mr. Warner. We did all kinds of physics stuff. Like, I know a popular one is like the egg drop experiment, where you have to build uh some structure out of very limited materials. Like for us, we could only use toothpicks and glue, and we had to drop an egg off of the stands, like the top row of the stands in the football stadium, and try to have it not break, not crack when it hits the bottom. So that was one of the most memorable experiments for me that really just took off my interest in physics.
Now I have to know, did yours break?
So yeah, the funny story is mine actually did break, which is hilarious because you'd think like, oh, he's a physicist. I'm sure his did one of the best. No, 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 no. Mine actually did break. The idea was good. It's just the execution wasn't there. We
Well,
had I was just gonna say I just had a ton of fun doing it, and I honestly, even if it like that moment that it broke, usually I would be like, I don't know, sad or frustrated that my project didn't work, but I was just laughing the whole time. And it's not like he didn't even give us a bad grade because he saw we tried, and he saw like our technique and stuff. So it was just a bunch of fun, and it encouraged me to to be okay with failing. And I think if everyone has something of that kind of experience, or I hope so, where like they can be okay with failing sometimes, and that's where you might learn the most a lot of times.
well, I think the unwritten rule is if you only have a 10%, if let me reverse it. If you have a 90% failure rate, you're actually doing pretty good. You're probably ahead of the curve. Like, I don't think a lot of non-scientists realize the level of failure that scientists have every day in their research.
Yep.
Like in biology, it's, in your case, it's, could be a satellite is no longer communicating or something. in our case, you can walk in and all your cells are contaminated. You could, the laser breaks for the microscope. I mean, there's so many things. A power pack breaks while you're doing a gel, and these samples that you spent weeks or even months preparing are all of a sudden just gone.
Yeah.
Yep. And this stuff happens all the time, and you have to be able to weather the storms because, well, that those few successes are mighty sweet.
That's true. All those failures make the successes even more tasty whenever they happen. Yeah.
Yeah, I agree. So what's it like working with a famous satellite's data, the JUNO satellite, that you get your hands on this data and that you can actually, you're allowed to work with it?
Yeah, it's fantastic. I going in to graduate school never would have thought that I'd be able to work with a satellite orbiting another planet. And here I am working on the JUNO mission, where it collects data, every day, every 30 seconds, and we get that data and interpret it week in and week out. And at first, it was a little daunting because huge learning curve where I'm joining the work of this mission in the middle of the mission. So I started working on it in maybe like, I think it was 2021, summer of 2021. And the mission has been active and at Jupiter since middle of 2017. So I'm working with colleagues who have been interpreting this data already for 4 years. And that's a good thing and a bad thing, because good thing is they at least can help me along the process and help me with this large learning curve. And then, of course, the bad thing is that there is this large learning curve that is, I'm kind of 4 years behind on. So that was kind of my first experience with it, and as more and more failures and successes accumulated, it's gotten easier and easier to interpret some of this plasma data and magnetic field data that's coming in from JUNO, which is mainly what it surveys. It also has a camera as well, which takes some pretty cool images. So
I've seen some of the images. I mean, you wish that satellite had the new cameras that we have, but since it was shipped out of orbit in probably 2010 or something, it's a little bit behind, but still amazing. So maybe we should talk about what the things are that it is measuring in a little bit of detail, like what is a magnetopause, what is a magnetosphere.
Right.
I think that, we kind of start from first principles and
Oh
work.
yeah.
Yeah.
So to know about a planet's sphere of influence, it's not just gravity that is influenced, or that the planet uses to influence other objects.
Careful, you might upset someone.
Yeah, right.
It is not gravity centric.
So we have each planet has or not every planet, but a lot of planets do have magnetic fields. The Earth does as well, and that's why we do have a North Pole and a South Pole. It's not just called that because someone decided to call it that. Is because it's a magnetic field term. So actually, for the Earth, our North Pole, our cardinal direction North Pole, is actually its magnetic South Pole, and vice versa.
Which has occurred because it's flip-flopped in the past.
Right. So it'll switch again eventually. I always like to kind of spout that little fun fact that right now it's backwards, but it will eventually switch back because it does that every now and again. So
which planets don't have a magnetosphere? Any in our solar system?
Yeah. So it's actually, and I'm sure you know about this too. A lot of topics with questions, even as simple as that, can be hotly debated. Um,
Well,
so
but that's what we're here for. I mean,
right,
the motto of the show is listen to experts, make your own decisions. This
yeah,
is not about right or wrong, trying to convince somebody per se. It's really just, you know, but talking, and there's opinions that have data behind both of them. And in the end, you're the one that gets to decide.
right. I would say there it's more the inner planets. So Mercury and Mars have very little or zero magnetosphere or magnetic field influence on their surroundings. Whereas a lot of the outer planets do have magnetospheres and larger ones. The Earth also has one, and I'm pretty sure I think Venus has one as well. So there's a couple that don't, but a lot of them do, and especially the outer planets.
What are the modern theories of how the magnetosphere is even generated?
Yeah, so a lot of it is from um, basically the rotating of the cores of inside the planet is called a dynamo, and essentially if you have changes in electric fields or magnetic fields, like they both go hand in hand, they affect each other, and you have all of this material inside of a planet. So take the Earth for instance, right? There's the mantle, the core, and all that stuff is shifting around. um, that creates this magnetic field that um, essentially is the North Pole is where there's a force going out from it, and then the South Pole is where those we call field lines that are kind of imaginary lines that particles would travel along due to this magnetic force. They follow those lines from the North Pole around the planet into the South Pole. So that's kind of the shape also of what a magnetosphere would be like. It's a sphere, mostly, not completely, and I can get into that a little bit as well. It's more teardrop shaped, uh, because we have these all these planets are revolving around the sun, um, moving quite fast too. And because of that, there's these bow shocks that it creates, just like if you were to look at an asteroid, right? You have the head of the asteroid, and then it has this tail um, on the opposite side of which opposite direction in which is traveling. And it's the same thing with the magnetosphere, that it takes the same shape. So we call the head of it the bow shock, and then the other the magneto tail. Pretty straightforward there.
And
So
these magnetic fields, they have to have an electrical component.
right,
That's,
absolutely, absolutely. Pretty
so
much any
what kind of a current strength are we talking about? Let's just say for the Earth, that's powering this magnetic field that is the savior of our planet by blocking all of the nasty radiation coming in from space.
yeah, yeah. It's got to be pretty strong. Definitely strong enough to exactly what you were saying, right? To hold off this solar radiation that's coming in. However, sometimes, depending on the activity on what the sun is doing, for instance, there's these events called the coronal mass ejection that can happen on the sun, where we get a wave of very powerful solar energy that is emitted towards outward, radially outward, which includes the Earth. We get these large scale power outages at Earth where the Earth's magnetosphere isn't able to completely hold that off. Luckily, it's just for a limited period of time because coronal mass ejections don't last a long time. It's just a big burst of energy. But it does have, real world effects on the planet, regarding the Earth's magnetosphere, the electrical currents around that, and as well as all the way back at the sun. So
So we just had one a couple days ago that knocked out radio transmission in all of North America for a short period of time.
that's right. We did. Exactly. Yeah. Great example.
And wasn't there an event, I don't know, 30 or 40 years ago that literally knocked out the energy grid for a short period of time?
Yeah, it did. It did. Yeah. There's actually uh, several companies that like their main job is to look at the sun's activity and predict not only when it could impact the Earth, but how much of an impact it will have based off of the solar activity that we see.
Well, maybe we'll get into that towards the end because there's some very interesting places to go with what kind of energies are coming out of the sun and hitting us.
Sure. Yeah, yeah, yeah.
But for the for just kind of everybody, uh, how do you see this like as a global force? I mean, people suggest that if we understand the magnetosphere, that we're likely to also understand things like volcanoes and volcanism much better, that this feeds into our atmosphere, that this also could be a major part of climate change in a lot of people's thoughts. What do you think about this?
Honestly, I don't know. That's the plain and simple truth. So I for what I've studied, I haven't looked at volcanic activities in relation to the magnetosphere of the Earth or other moons, I guess, because there's this like for instance, Io is a very volcanically
That's kind of
active
what I was
moon.
referring to is in Jupiter. I mean, it's very clear that Io has this plasma slash magnetic slash
Yeah,
electrical
I do. Yes,
interaction with Jupiter, that and Io is filled with volcanic activity
right.
of some kind.
Yeah, I
So
do know a lot about that. At least more than the average.
the
You
average
know,
beaver.
average beaver. Yeah, there you go. But yeah, because that does play a pretty big role into Jupiter's system. Io is one of the four Galilean moons, and just basically one of the four large, most recognizable moons at Jupiter. That's essentially all it means. There's some history to that too, but yeah, Io is very highly volcanically active, and this all these volcanoes spew out sulfur into um, Jupiter's orbit, and so this makes this torus shape eventually, just due to gravitational forces and magnetosphere forces as well, which does have an impact on the measurements that Juno receives, and basically we're able to measure sulfur and oxygen particles as we get closer and closer to Jupiter, due to mainly Io and its volcanic activity.
It's
Uh,
putting out like 1 ton of material a second,
per
right?
second, that's right.
So per
It,
second, yeah.
it's ridiculous. Yes, it's a ridiculous amount of material, definitely.
You would think that the moon would be gone. If it's
You would
putting out
think.
a ton a second, doesn't that
Yeah.
also mean it has to be pulling in from somewhere or it literally would have evaporated?
I think that there has to be a certain point to where either these volcanoes just can no longer be active, they've run out of their active phase, or um or something else to where the mass of Io is significantly impacted to where a lot of other things may be happening more so than just the volcanic activity.
So let's actually discuss kind of what you were working on,
Sure.
because what's really interesting to me is that uh, you're studying these things called Kelvin-Holtzman instabilities.
Right.
And where you're looking for them is in the as Juno, the spacecraft, crosses the magnetopause, which to my understanding is where the magnetic field that is generated by the solar wind meets the magnetic field of Jupiter, and
Mm-hmm.
in the space where they are not mixing,
Right.
or not mixing at volume.
At volume,
This
yes.
this is the magnetopause.
Yeah, that's correct. So you have essentially Jupiter's magnetic field and the sun's magnetic field. There are also the emitted particles from the sun called the solar wind, which is a pretty constant stream of particles that are moving at about 400 kilometers per second. And this clashing point where Jupiter's magnetic field is able to hold off these particles is, yeah, what we call the magnetopause. Exactly. And there's usually uh the some of the easiest features to look for when um recognizing or being able to recognize the magnetic or magnetopause is the large changes in magnetic field, as well as its direction. So we have like if the Jupiter's magnetic field is the opposite of the Earth's. So its north pole is actually its magnetic north pole. So essentially, particles far out from Jupiter and near its equatorial region should be the magnetic field should be pointing downward, or southward. And so that is one instance, one feature to look for when we get into Jupiter's magnetosphere. And so when we cross the magnetopause, we'll see that shift from solar like magnetic field, which usually isn't as strong southward of a magnetic field component, to a very strong southward magnetic field component.
So when Jupiter's or Juno is orbiting,
Mm-hmm.
it doesn't always pass through the magnetopause, right?
Correct. It did for quite some time though. Starting at the missions, at inbound, in 2017, it crossed the magnetopause, of course, to be inbound and start orbiting Jupiter. And the way that Juno orbits Jupiter is very um it it has a very eccentric orbit. So you start very far out and then you go very, very close to Jupiter, and then it gets slingshot back out really far again. And it's been doing this and also processing around the planet for a few years, um, up until about middle of 2018. So until middle of 2018, it would cross the magnetopause every single time that it goes on the outbound part, the apogee as we call it, or apogee for Earth. Some people might know more popularly. And after that point, it gets too far back. If you're looking at the sun, and then there's Jupiter, sun's on the left, then Jupiter on the right. It goes far enough right into the magnetotail part to where the magnetopause is too far away from where Juno is, and then we haven't seen it since recently, where it's come all the way back around the other side, the backside, and now we're starting to see magnetopause crossings again.
So it's due to the precession that it went through the magnetopause, and then it went through the magnetotail, and then
Yeah.
now it's coming back to the magnetopause.
Right. Right. Yeah.
Okay.
Exactly.
So you were with so all the data in your paper, is that mostly from the 2017 2018 data set?
That's right. Yes. It's from that first part. We call it the dawn side uh, of Jupiter, which is essentially, as Jupiter's rotating, it would be dawn. For if people were to be there, we would see, the sun rising on the horizon. Yeah.
So now is it in the sunset region?
Right.
Is
Yeah, it's on the dusk side.
the
Yep.
dust side? Okay.
Hmm.
So obviously, then you're already starting a new paper because you did.
Yeah, so my one of my colleagues is looking at the new magnetopause crossings, and these are slightly different because the ones that I looked at were in the equatorial region. The ones that these are in are not only on the opposite side, but they're also not in the equatorial region. They're further southward. We call it higher latitudes. They're at higher latitudes than, yeah, in the
That makes
equatorial region.
sense. So
So,
closer to the South Pole.
correct. Yeah, yeah, yeah. And I'm planning on being a co-author for that paper, but I'm actually working on rounding out the analysis of the dawn side. I'm on my third paper of the dawn side magnetopause crossings, and I'm looking at two different physical processes and one uh, more physical region and characterizing a specific region. But we can get into that later.
For
I
sure.
Yeah, I also heard you mentioned Kelvin-Helmholtz instabilities, and that was, yeah, my most recent paper that I published, which is quite fascinating.
Well, I'll put up some pictures of what they are. Why don't you tell us what they are?
Sure. Yeah, that helps definitely. I think a
This
picture is almost a must when describing this. Yeah, because it doesn't just happen in space. It can happen anywhere where there's two different density fluids interacting with each other. So that's the start of it, right? You have two different fluids that are of different densities, and they're moving in different directions. Well, relatively.
relative
So
relative because it they can't even be caused from two fluids or gases, heavy enough gases flowing in the same direction, but one is just significantly faster than the other one.
exactly, exactly. That's very well put. It's the easiest to picture, at least in your mind, if they're going in opposite directions, but it definitely can occur if they're going in the same direction. As long as one is going much faster than the other, there just has to be a big velocity difference. And when you have this large velocity difference, as well as any sort of perturbation in the boundary that separates these two fluids, then that perturbation will essentially grow first linearly and then non-linearly. So there's linear and non-linear. KHI is the easy way to say it. Say that. But basically, they end up uh, forming or sort of mixing their momentum with the other fluid and rolling up around each other and creating these vortexes, these wave-like structures known as KH waves or Kelvin-Helmholtz waves.
I mean,
So,
it's probable that if you're over 40, you've probably seen them in clouds once in your life. They're not that uncommon in the clouds that you don't see those perfect little curly cues that appear to be riding on top of cumulus clouds.
yeah, absolutely. Absolutely. That it happens in clouds even, right? So, anyone could have experienced actually seeing this by eye. Of course, at Jupiter, um, it's a little different, and you can't view it by eye, but there's other ways to observe these things.
Well,
And
some of them you can in the planet gas, right? Because you can see the little curly cues on the surface, or what we see as the surface.
yes,
You can see them sometimes.
right, right, that's true. Like if you're looking at the atmosphere of
Mm-hmm.
Jupiter or any other planet that has different densities in their atmosphere, yeah, definitely. Uh, so we see these waves occurring at the magnetopause, at least on the dawn side. Uh, and that alone is a big discovery because it was always hypothesized that it would happen at Jupiter, and since we already talked about this, all these volcanic gases from Io being ejected into Jupiter's magnetosphere. That we consider, by the way, a fluid. Like a lot of plasma physics, we just consider fluids because a fluid in our definition is essentially a group of particles that has collective behavior. And so as long as it fits
Well,
that.
then plasma is a clearly a fluid in that case, if that's your
Right, right.
definition.
Yeah. The Io and Jupiter plasma mixing with the solar wind, right? The sun's plasma, two different fluids that's where
Okay,
those
I got to
come
stop
from.
you there for 1 second.
Sure.
So you will say, or in your opinion, the solar wind is a plasma wind.
Yes, yes. It
Okay,
I
because that's
yeah.
also something that might get us both censored.
Okay,
But
okay. Fair.
uh,
That's what science is about, right? Like we don't have to. No one has to agree with anyone else, but I try to respect other people's opinions
of
or
course, of course,
their sides of their arguments and try to see where they're coming from. I think that makes us all better as a scientific community.
100%. I mean, to think about the amount of energy alone that comes out of the sun, and to think about how much energy we can measure, how much that energy is, requires an incredible amount of charged particles. So then to think that uh, this is not creating a plasma itself that then is the solar wind that's flowing. I mean, I see it from your perspective. Now, I see other perspectives as well,
Mm-hmm.
and maybe we'll get into those later too.
Sure.
But for the purposes of our discussion, let's call it a plasma, and that it because it makes it also easier to understand why these Kelvin-Helmholtz, the KHIs, are so important. Or because the videos that I was watching in the seminars, they were talking about it as if it was just known that they were going to be there all the way back in 2017.
Mm-hmm.
So before you even had the data,
Right.
they were already convinced that they were there.
Yep. Yeah. Uh, they were definitely convinced they were there. There's several papers I've read that they're saying the same thing, and they're modeling and simulation papers, and they're like, look, we ran some of our initial conditions. This is what happens. Um, so I think it's a good next step that we actually have the data now, and we've done the data analysis to say, look, it's actually happening. This isn't models, this isn't simulation, but it's confirming these hypotheses that yes, Kelvin-Helmholtz waves do occur at Jupiter. Uh, and there's some scientists that kind of put a taboo on Kelvin-Helmholtz instabilities. Not that they don't think it exists, but they they have a very very high standard of what you need to say that KHI does exist and is happening at certain planets. They're more so on the side of magnetic reconnection, which is the other process I've
Well,
studied.
we're definitely getting into that because that's
Okay.
where it gets really juicy.
Yes. Yes. That's a big topic, very popular topic. I went to a conference this summer that was two-thirds talking about magnetic reconnection. So a lot of people are very much into that. Yes.
But your measurements of these KHIs, part of it was geared towards seeing whether or not magnetic reconnections happen or not. So maybe we should
Sure.
describe what a magnetic reconnection is and why KHIs are the place to look for that type of a thing.
Yeah. Yeah. I did sort of do some overlap with magnetic reconnection. You're right there. And essentially what magnetic reconnection is where two magnetic fields um, are Intersecting. They end up intersecting with one another, which is it's not, I mean, it's not like a super regular occurrence in everyday life that this happens. And so whenever these magnetic fields intersect, it's kind of, it wants to get back to this sort of equilibrium uh with the magnetic fields. Magnetic fields aren't really supposed to intersect, and so they want to get back to being curved and sort of bubbly, I guess is another descriptor word. So they intersect for a split second, and they merge in different ways and sort of reconstruct themselves to fit back with these different or regularly programmed magnetic field configurations, to where, like, if you have two magnetic fields colliding or clashing with one another, then like let's say in the negative x and positive x direction, then they reconnect and remerge. Then you'll have particles ejected in the positive z and negative z directions. So in a completely different direction, basically squeezed out.
Squeezing out
Yeah.
the energy that
Mm-hmm.
is actually kind of a, I guess for lack of a better term, an overflow that doesn't fit within the field neatly. So then this creates an electric field sheet. Is that correct?
Yeah, there's this it's called a frozen in condition for the particles. So basically, this frozen in condition is where particles travel along magnetic field lines, and it breaks that condition in this sort of diffusion region, we call it. And whenever it breaks this frozen in condition, these particles say, you know what? No, we're not going to behave. We can't follow these magnetic field lines anymore. We have to get out of here. So all this magnetic energy becomes particle kinetic energy and is forced into the particles, ejects them. Now there are large fluctuations in the electric field as well, and that's actually one of the big telltale signs that magnetic reconnection is happening. You'll see this large spike and drop from the electric field, and a lot of papers say, look, we see this, so magnetic reconnection, there's at least some evidence that it's happening right here. Mm-hmm.
So why is magnetic reconnection important? Why should we even care? So the field lines move around a little bit. Like, why is magnetic reconnection even a thing? And why are people so quick to contest each other over this phenomenon?
Yeah, that's a big question.
It is,
I
but we
think
can handle it.
we can. So that's a big question, not even in my field, just like in any field of science, or even outside of science. Why do we care, right? That's the question that should be answered in any field of study. And so for magnetic reconnection, it affects how particles are transported, and energy, so mass and energy, are transported from one region of space to another region of space. And this can affect each space environment separately, right? So magnetic reconnection occurs at Earth, it occurs at Jupiter, a lot of planets with magnetospheres. Particles can be injected, so like solar wind particles can be injected into, let's say, Earth's magnetosphere, and particles in Earth's magnetosphere can be ejected out of its magnetosphere. And this sort of process is essentially it's a fundamental process of physics that is worth understanding, because it can transport mass and energy from one region of space to another. Now, there are studies also about how these injected solar wind particles, like how far do they travel and where do they travel? some say they can even travel all the way into Earth's atmosphere, more towards the North or South Pole. Um, but that it's somewhat newer in science for those studies, but that's one reason that it's important, and it does affect KHI as well, because these waves are twisting themselves, and so it also twists the magnetic field, and this twisting in the magnetic field can cause these magnetic field lines to again reconnect and merge, and magnetic reconnection can occur when that happens.
So, because kind of the way I understand it is that uh, when you're talking about as much energy as we're talking about, and then at the planetary scale, we're talking, you know, megawatts, more than that, like real planetary scale size electric currents.
Yep.
That when these reconnection events occur, that energy, if it's not just perfectly translated into the magnetic field, into the electric current, there's going to be energy that has to go somewhere else because
Of
it's not
course.
neatly fitting into these things.
Right.
And that energy could cause ionization, further ionization of other particles. And my vision of it is, if for some reason a part of the Earth's magnetic field broke down even momentarily, it could be that uh, through these connections with the sun and with the solar wind, that you could have something really catastrophic happen where all of this excess energy just starts flying out everywhere and just stripping the Earth of its atmosphere. I mean, this would be like one of the movie scenarios that could happen. That would be, great movie plot, actually.
Right. I would say a more realistic movie scenario than most, though, like it's physics based, physics founded. So yeah.
Yeah. So, I mean, at a scale that people could actually, wrap their heads around, if you're not a physicist, that's the kind of stuff that we're talking about. So it's really important to understand why, first of all, how much energy is coming in, where is it going, why does it do what it does, and then what can we learn from it that maybe we can use it to our advantage. Maybe Tesla was onto something. And then, well, because it's kind of what he was proposing.
Mm-hmm.
I mean, it's kind of what he was proposing, but also just to understand the structure of our solar system, which I don't think most average people know is still completely unsettled.
Right.
Why the planets are in the order they're in, how they got that way. And I mean, even things like, as a little aside, even things like accretion disks, like it's hard to wrap your head around accretion disks making planets. But, this is the standard model, and okay.
Yep.
But all of these other forces, such as the magnetospheres, such as the interactions that they have through what you're calling magnetic reconnection, would all be ongoing during these processes across the solar system.
Yeah. And beyond too.
And beyond.
Any other star system as well. Or anything that has a magnetic field of its own. So it can help us learn about not just our planet, not just our solar system, but the universe, and how physics works more so, in the rest of the universe. And I think that sometimes it can be lost on us that itself is still important, to know how the world works, how the universe works, from these large scale events happening all the way down to this, like microbiology. Like all of that is extremely important, and we may not see the end picture of how exactly important it is right now, but these steps are still just as important as the end result.
All fundamentals are just that, fundamentals.
Yep.
And you cannot build your pyramid of science, of understanding our reality, without solid fundamentals.
Right.
And given that, also, I don't think, what I was amazed about when I was studying up on this is the complexity of the magnetosphere. There's like, what, 12, 15 different populations of different ions and electrons at different
Yep.
energy ranges across different latitudes.
Different
And
types of ionizations, all of this. Yeah. It's
yes,
ridiculous.
so it's not hard to understand why we don't understand it.
Hmm.
That's the easy part, because it's actually very complex.
Hmm.
But maybe you could explain to me why, or how your findings from JUNO add a little extra, uh, a little bit of extra known to the unknown, because it really does.
Yeah. Yeah, definitely. I think that one of our main findings at JUNO and for this specific study is that it's how common this process or these few processes can be. Because at Earth we're it's a bias, of course. We're able to study the Earth the most out of all the planets everywhere else because we live here, right? And so we're able to study these processes in more detail because, yeah, of course, it's not going to, first off, cost as much to have a satellite orbit Earth versus a satellite orbiting Jupiter. It's also not going to be as hard to argue for a mission about Earth versus a mission about Jupiter because, again, we live here. That's a big argument for studying Earth. However, there's some processes that don't happen at Earth, or at least don't happen as often at Earth that they do at other planets.
Or they don't happen at a scale that's as easily measured.
Exactly, exactly. And so for KHI, uh, if it happens at Earth, it happens very rarely, and it's more so magnetic reconnection driven of a system than other planets. But we wouldn't have known that unless we went out and studied and put missions out at Jupiter and at Saturn. Uh, with Cassini at Saturn and Juno at Jupiter. Unless we did
If
that,
we get a second to talk about Cassini, that stuff is wild. I
yeah,
love it.
yeah. And so those two missions a lot of times I see going hand in hand in how it helps us understand the larger context outside of just Earth and how for further space exploration how much we can learn from just studying Jupiter and Saturn because those are wildly different planets than Earth is, and any other inner planet is, right? The inner planets are more rocky and smaller, of course, than the outer planets, which are more gaseous and larger scale, like you were saying.
So your research, though, like, really, this was the kind of the take home message that I got, and you can correct me and or expound upon
Sure.
what I got. But what I got was that the the KHI events are happening as it's crossing the magnetopause somewhat regularly, and in doing so, they are allowing for, or I don't want to say creating, but it is kind of creating, and because this is where you'll correct me, it that sometimes KHIs do create magnetic reconnection events locally, which could be a way that this energy that is moving across the magnetopause is safely moved into the planetary environment. And so you did see this evidence for magnetic reconnection in the KHI events, but not all KHI events contained a magnetic reconnection event where you could observe it.
Correct. Absolutely correct. Yeah. I
So,
think, yeah, go ahead.
so given that the energy's still coming in, it's still causing the KHI instabilities that are causing the curling of these plasma rings that are then contorting the magnetosphere into God knows how many different shapes, could be four-dimensional shapes for all we know. And that those areas, what happens in those areas during the time that that flux is going on? Are there any like major events? Are there major energy releases? Does it cause any effects on the atmosphere? Like what happens in those areas when it's really in the throes of creating the KHI instability and you're getting kind of the strongest twisting of the magnetic fields beyond just causing, or not necessarily causing, but being associated with some magnetic reconnection events?
Yeah, I think that in the strongest cases, these waves that occur at the magnetopause um, are massive, like in size. But I mean, and in mass as well, literally.
Tell us this, just so people have an idea.
Yeah, of course. So these are several. You could put several Jupiters within these waves that occur at the
Oh,
magnetopause.
so they're just gigantic.
Yeah, right. And yeah, obviously, for those who don't know, Jupiter is the largest planet in our solar system, and you can put several of them within these waves. So there's tons and
You can put
tons
like
of matter.
43 Earths inside of Jupiter, right?
Right. Yeah.
Yeah.
Yeah. So if you can put several Jupiters inside of these waves, you can try to wrap your head around the scale size of these Kelvin-Helmholtz waves. And that's that's what it is at its strongest, where you have these massive vortices twisting along the magnetopause, starting at what we call the subsolar point, where you can draw basically a line from Jupiter straight to the sun. That's the subsolar point, and you put it at the magnetopause. Um, Going along the magnetopause, along in tailward, uh, that's how these waves grow and develop. So they'll start closer to the subsolar point, not necessarily at the subsolar point, but close to it, where you have this boundary starting to kind of wiggle a little bit, be perturbed, and it continues to grow and grow and grow until right at what we call the dawn terminator, where basically like you cut Jupiter in half to where you have the sunlit side and then the dark side, and you draw a line up that's where um, it can be the largest, the most turbulent between all the different kinds of plasmas that are in there, which is mainly solar wind material and iogenic material. And so you have these massive waves that can fit several Jupiters inside, that started off, less than the size of Jupiter, very, very small, has to start somewhere. But they grow and develop over time all the way down the magnetopause until there's a massive amount of mixing in the boundary layer, or at the magnetopause.
So I wasn't aware that of the scale of this, because when you look at the data, it's hard to really put your head around the scales that you're looking at. But
Right.
given that, then the magnetic reconnections that you observed near these Kelvin, the KHIs, some of these have to be enormous. Do these produce any type of jets or plasmoids,
Mm,
or is there anything going on there during the magnetic reconnection? Or is
yeah.
this where the field lines really just meld together and there's a more clean energy transfer?
Right. So I think that for the instances where we observe magnetic reconnection, there are jets that are observed. Now, uh, jets could be a broad term for different kinds of scientists. These we call reconnection jets, and essentially we see their velocities spike, um, which and spike in different directions than they were originally traveling. So, and that's because of this magnetic reconnection effect.
It
Um,
has to go in the opposite direction.
yeah, exactly.
Has
And
to.
we see that via being able to observe their velocities, these different kinds of velocities occurring. So from the reconnection events, we do see the jets. Besides the reconnection events, I think there were maybe like six in total of like 60 or so magnetopause crossings, 62. And without the reconnection events, it's essentially you can picture back to the clouds example where the cloud, this water vapor is mixing with the air, except on a much larger scale, where it's just essentially a lot of turbulence, but then eventually they will get put back on their respective magnetic field lines, whether they end up on one side of the magnetopause or the other side, and then go on their separate ways. Um,
So,
that can eventually affect the planet or yeah, the heliosphere.
okay, before I get there, because I
Okay,
want to have just a couple more questions on your work. And
sure.
then I'm hoping you have a little bit of time to go exploring down some rabbit holes.
Okay.
So, uh, given that you don't always see magnetic reconnection, you state in the paper that it could be happening, you're just not seeing it. It's happening somewhere outside of your vision. Now, what if that's, first of all, do you think that's what's going on? And if not, why are we getting this incredible turbulence yet not seeing a mixing of the two different well, not magnetospheres, but magnetic fields?
Mm. So I think, well, I
And you
think
didn't think a
that
biologist would come with these kind of questions, huh?
no, honestly, I think anyone with enough curiosity can come up with really good questions. So these are really good. I think that it's not, I think that it definitely is happening elsewhere at Jupiter. After a certain point, magnetic reconnection, like in certain locations, magnetic reconnection is more likely to happen than other locations. So basically, at the subsolar point at Earth, and most likely at Jupiter, it's most likely to happen because that's where the magnetic fields clash the most. Um, as you go farther and farther down the magnetopause, and this might help answer your follow up question, the magnetic field of the sun, which you're still correct by the way by saying it's magnetosphere. It's just the sun has a magnet. It's kind of like interchangeable.
Okay,
Uh,
because there's the heliopause, but that's not. Would you consider the heliopause the entire space of the magnetosphere of the sun? Anything that's inside the heliopause?
yeah, I would consider it. Yeah.
Okay, so for
Mhm.
anybody that doesn't know, the heliopause is how far outside Pluto? Like
It's way out there.
it's
Like
way outside of any of the planets. It's
we
like
just, yeah, we just witnessed Voyager. I don't know, sent some like relatively recently crossed the heliopause, and we sent that thing out so long ago. So
in the 60s or the 70s.
I can't remember.
I think it's the
But
70s.
I think it was the 70s too.
So it's been going for 50 years
Yeah, and it just crossed the
at a rate
heliopause.
of like 17 or 20,000 miles an hour, something
Hmm.
like this.
Yeah,
And
yeah,
it just 50 years later got out of the sun's magnetosphere so that
right.
everybody can understand like this is just so far out there.
Yeah, so
Okay.
far out there. So as you go farther from the solar subsolar point and closer to the actual dawn terminator, the dawn side and more tailward than that. This magnetic field of the sun is sort of just draping over the magnetic field of Jupiter instead of clashing head on with it. So that's a reason why it's less likely that magnetic reconnection would happen on, farther and farther down Jupiter's magnetopause, because there's not as much force clashing with one another, and that's what you need for magnetic reconnection to occur, at least part of it.
So, what are the questions that you were left with? Like, you learn that these beautiful waves that are the size of multiple Jupiters happen, and that there's this relationship becomes not clear, but certainly there's some type of process that these magnetic reconnections and KHIs can occur simultaneously, and maybe are always simultaneous but occurring in other parts that you don't see. What questions were you left for, or what are you hoping to get out of your new data analysis?
Right. Lots of questions for sure. So one of the questions I have was, what does it look like on the dusk side? Are these KH waves the same in intensity and frequency, or are they different in both? Because they're hypothesized to be both on both the dawn side and the dusk side of Jupiter, and they're also hypothesized to be shaped a certain way throughout, like regardless of if they're on the dusk side or the dawn side, because it was previously hypothesized that the sulfur material that orbits around Jupiter continues to do so even near Jupiter's magnetopause, which is about 50 Jupiters away from Jupiter, FYI, for like the scaling again. That might help. Yeah, I should have mentioned that earlier, but it's about 50 Jupiters away from Jupiter itself. That's where the magnetopause is located. It's been hypothesized that these KH waves were all kind of looping and swirling in the same direction because of the orbit of this sulfurous material. All again looping in a certain direction, the same as the way Jupiter rotates. However, a finding that we found in this study is that that's not the case. So the velocities that we were getting at JUNO near the magnetopause were not orbiting with Jupiter. They weren't co-rotating with Jupiter. They were more so in line with still the direction that the solar wind was traveling, just less of a magnitude.
So that brings up a very interesting part of plasma physics. So I want to let you finish, and then let's really get. Actually, no. Let's talk about it now. Okay. So because these counter rotational rings, because it's kind of what we're talking about.
Mm-hmm.
They are the one place that they are always observed, and comes from physics that's 100 years old, are Birkeland currents.
Mm-hmm.
So is there a potential that what we're seeing is plasma coming from the sun in a Birkeland current, that's the solar wind, and that's why you see these counter-rotational energies, because of the different ionizations that occur at all the different places, and Birkeland currents would predict that each of those different populations would be segregated within the current, and that they would rotate counter-rotationally, that each ring would rotate counter-rotation to the other one.
Right. And that's, I guess that's another question you could just add on to the end of that study, right? Like, that's a hypothesis that comes out of that. And there's just looking at these processes, just two processes, right? You could look at KHI and magnetic reconnection and how they're related. So many questions can pop out from that. So many ideas can pop out from that. Like you suggested with the counter-rotational flows. And I think there's just, since there's more than one process occurring at Jupiter, there's an exponential amount more questions that stem because those two processes are occurring. And so one of those is, why are these counter rotational flows happening? Like, when it's been hypothesized for several years that they shouldn't be rotating like this, they shouldn't be traveling in this direction. Um, why are KH waves not, like, could they be similarly shape or the same shape regardless of if they're on the dawn side or the dusk side, or do they wrap up in different directions? Do they, swirl in different directions, so to speak, because of these different flows that we found? I'm thinking maybe they do rotate differently than we previously thought. uh
Be exciting if they did.
I
I
think
mean, it
so.
doesn't ruin anything if they didn't. It's just
Right.
science. I'm just trying to
Yeah.
understand. But it would be interesting if they did, because it would call into question a lot of the modeling that's being used. And I mean, this is how we do science. And some models prevail and some models, move to the wayside as additional data becomes available.
Yeah, and I think as both a modeler or a data analyst, you have to be flexible in what new observations come out. You have to be open-minded in that, oh, this scientist found something that was different from what I had. Why is that? Like, try not to get discouraged or offended that it's different. It's just science, like you were saying. That's all it is. We're all learning here at the end of the day.
Well, this is why I'm doing this show. I mean,
Yeah.
it really is. I feel like scientific discourse in this country has become like political discourse. And it was never meant to be that.
No,
It was
I agree
never meant to
100%.
be that the goal of debating was to tear down your opponent. That if that would have been the case, we would have never gotten a Copenhagen interpretation. And we still don't know if that's right.
Hmm.
So, but at least back then, and they may have been arguing like mad behind closed doors. But when the actual language that they wanted to present as scientists came out, it had none of that nonsense in it. Today, it seems like it's just the goal. It's like, how quickly can I tear you down and tear down your argument? Sometimes it seems like even at the expense of the truth.
Yes. Yes.
And this is where, and we wonder why people have such a low opinion of scientists these days. It's kind of earned a
Yep.
little bit earned,
Yeah.
that we're too busy squabbling to
Hmm.
be like, you have a point and you have data to support it. You have a point and you have data to support it. You have a model that uses that data and says this. I have a model that uses that same data and says this.
Hmm.
We should be able to critique both of our models, and at the end, because we don't know, agree to disagree until further data is obtained, that then one model starts to become more favorable than another.
Right. And I think that not only should we be okay with agreeing to disagree, I think we should also agree to figure this out more cooperatively than competitively, right?
Yes. Well, unfortunately, because of the way they've made funding, this is an impossibility.
Yeah.
Because I heard somebody else say it. It might have been Pavel. I heard him say recently that the dumbest thing that was ever done is to make scientists compete for funding.
Mhm.
And I couldn't agree more. And why? Because that's how I did it. Like,
Yeah.
I'm a competitive motherfucker. You know
Yeah.
what I mean?
Yeah, me too.
And you have
Hmm.
to be, because if not, you'll never get you'll never get the funding, you'll never get the big publications, you'll never get. And you have to have all those things to be competitive to get funding. So in the end, it's all driven by the funding. If I had not been in that state of mind and in the state of mind that I'm in now, I am thoroughly convinced that I would have done 10x what I did in the same amount of time 20 years ago.
Yeah. Yeah. But like if you maybe you wouldn't have gotten the funding, right? Because that's how the world works. Like it's just yeah. I know what you're saying. Yeah.
Yeah, and it's hard. And
Unfortunate.
I feel for your generation the most. Like, hey, I love talking to young scientists, and I do, because you're not dyed in the wool yet. So I mean, tend to be a lot more open to new ideas, tend to be a little less, or even a lot less dogmatic, and also trying to be positive about the future.
Hmm.
And I feel like that, the conversation that you and I are having, this is what I hope becomes the norm
I do
again.
too.
I really do, because you can agree to disagree, and you can help somebody. You can even help somebody you don't agree with.
Yeah.
It's okay to
That's
give
fine.
them data. Like, data hoarding is the worst thing. Okay, I'm going to
Hmm.
actually ask you, because I know what data hoarding is like in biology, especially with protein sequences and genetic sequences and all this. What is data hoarding like in the physics world? Because I know
Yeah,
it has to happen.
it does. It's so for in the physics world, from what I've experienced so far, it's very what's the word? It's very undertoned, I guess. It's loudly subtle in a way where okay, like a couple years ago, we had a close flyby of Europa with JUNO. And so this was going to produce a lot of new science because it would be the closest we've ever been to Europa, the moon. Um, and so since it was very exciting, very new, easy science to produce, lots of questions already flying before we even got there. Um, we had to have several meetings for several weeks, probably anywhere between 2 weeks and a month of meetings every other day to weed out who's doing what. Because if we didn't do that, it would devolve into not only chaos, but so much competitiveness that there'd be fighting and arguing left and right over whose data is whose. So there's definitely data hoarding 100% in the physics world as well.
Yeah, and it's just awful, because
Mm-hmm.
it should be, so what if you and I take the same data and go off and do even the same question? I promise you there will still be two different answers, even if they're subtly different.
Mm-hmm.
And what's wrong with reproducibility?
Yeah.
Because
Yeah.
what is it? It's that, oh, I got it out first. Big deal. No one
Mm-hmm.
cares about first unless it ends up being true.
Yeah.
The first room temperature superconductor was just discovered a week ago, and guess what? That's how long it lasted. 1 week,
Mm-hmm.
because it's not true.
Right.
So
Right.
what is this being first? It's actually it, it's almost to your detriment,
It is.
because if you're first, guess what? If you're not right, you're the one that takes the fall. And oh, wait, you dragged how many other scientists and their research money and their funding, because they tried to reproduce your event and they couldn't do it. So, how much money did you waste? Like,
Yeah.
you can't even calculate it. Yet, this goes on all the time. You and
Yes.
I both know that about half of what gets published, maybe even a little less than half, maybe a lot less than half actually, ultimately ends up being correct.
Hmm.
but it's the best we could do for now. And that's a fine thing. And I agree with that.
Hmm.
However, with all of this big data, and it happens in physics, it happens in psychology, it happens in genetics, the number of people falsifying data has gone through the roof.
Mm.
And why? Because they need funding.
Yeah.
And then you need to be first, and you need to get the accolades so that you can get the money.
Yep. That's what it comes down to. Yeah.
Well, let's get out of that for a second. It's very depressing.
Okay. Sure.
So let me ask you just a couple of like global questions
Okay.
of like, and we can just chop it up for another minute or two.
Okay.
But we talked about magnetic reconnection a lot, and that this is a way of the sun plasma interacting with, in the sun's magnetosphere, interacting with planets. Is it really magnetic reconnection, or is it always connected and we see additional connections form and dissolve during these other events? And I ask that because when you look at even Jupiter, Saturn, especially Uranus, Neptune, the temperatures measured on the surface so far exceed what you could expect from just light that it appears there needs to be some type of plasma current,
Interaction. Yeah.
plasma interaction that is continuous to keep planetary temperatures where they are.
Right. That goes back to what you were saying earlier, where there's in physics, when it all, it all boils down to energy and energy conservation, where like this energy can't come out of nowhere, right? There has to be some other energy source that's providing this excess temperature to the planet. Um, but you can extrapolate that to almost any physics problem. Where's the mass going? Where's the energy going? Is the mass being converted to energy? And then energy is the bottom line. So energy has to be conserved throughout. And if it's not, then you're missing something. That it's a law of physics. So that that question that you had about, could this be coming from plasma interactions? Yeah, it could, because it can't just be if it's not just from light. Like we have pretty solid calculations on how much energy and how much heat light can produce, based off of distance, a distance to temperature relation. So we have that pretty solidified. But there's other things then that aren't solidified. And what are those factors that play into it? Could it be plasma interaction? Could it be something within the planet? Could it be atmospheric processes? We don't know.
Yeah, that's great to hear. So that this is, at least to your generation, it's still an open question.
Yes.
I think the farther you go up the age scale, it becomes more quote unquote settled. But so if there's more, so how deep are you into just plasma physics as a whole? Is this kind of like your sweet spot, one of the things you really work in?
I This is my sweet spot. However, I have previously been interested in some astrophysics as well, um, cosmology type stuff. I've taken a few classes on that, and a couple of quantum classes as well.
So here's my question then, because you're a plasma guy.
Yeah.
What do you think, given that like the torus that's around Jupiter is something that you see in the lab when you induce a current through plasmas? It's actually a very common shape to get. You get the hourglass with the torus around it,
Mm.
and then even at like the pole of Saturn is a hexagon, which is wild. I mean, it's a perfectly geometrical hexagon,
Yeah.
which is another shape that you can get on the pole of a cylinder, of a sphere that is being charged with plasma.
Mm-hmm.
So are we maybe underestimated? Do you think there is an underestimation in uh, the current literature? Maybe is the easiest. Do you think there's an underestimation about how many roles plasma can have outside of just gravitational theorems? That
Oh yeah.
maybe some of the gravitational things that are being attributed to gravity, maybe some of them can be attributed to plasma?
I absolutely agree. I think that as far as all physics topics go, plasma physics is one of the newest subfields of physics, and so I think compared to kinetics, gravitation, electrodynamics, um, there's a lot less that we know about plasma physics than than those other subfields. And so I think that definitely plasma could play a larger role than it's letting on right now, and that our literature is definitely incomplete. There's much more literature to be done, much more research to be done on plasma physics and plasma interactions in planetary environments.
I couldn't agree more. I think that because of the drive to maintain the Big Bang theory, I think that, for lack of a better term, like plasma physics has kind of been shit on.
Mm-hmm.
I kind of see that. I mean, I'm an outsider looking in. So for me, when I go through the literature and I'm reading things, and, in speaking with people that are on the side of the standard model, which of cosmology, which once
Mm-hmm.
again, I don't know. I don't know.
Mm-hmm.
But I like to ask questions.
I don't either. Yeah.
But I like to ask questions. And you do find that uh, there's a tone about people when you say, well, I'm not sure about the Big Bang. It's almost like you farted at a wedding sometimes.
Yeah.
It's kind of like that sometimes.
Mm-hmm.
And uh, what I hope is that we can get back to the Big Bang as a theory. There are many things that you could see that the data viewed from that model can support, but that doesn't mean there's not another model where those same things occur and it also supports that model.
Mm-hmm. Yeah.
And I think that that's where we get kind of lost as scientists sometimes, that we don't we have our model and this is the model, and it's like, well, but if you have another model that's all those things satisfy as well, I mean, you can make simple models
Mm-hmm.
with, paints and colors, and you
Yeah.
can say that, well, if my model is that if you put these colors together this way, this is what you get.
Mm-hmm.
And this is how you get to this, is through this path. You'd be like, well, my model is you use these different colors, and guess what? You still end up with the same color.
Mm-hmm. Yeah. I
And they're both okay. And in that case, you actually know what the answer is. They're both right.
mm-hmm.
But in physics, they can't both be right.
Yep.
So, but until we know, who knows?
Right. I think with models and simulations, constraints are everything for those. Initial conditions and constraints are everything. And that's where data and data analysis meets modeling, where you have to have sufficient data to provide those initial conditions for your models, for your simulations, in order for it to be accurate and as truthful as it can be, as true to science as it can be. If, like, for instance, for that example that I talked about, where we don't observe the velocities of the plasma that everyone else thought we would observe, So, and that was a constraint. That was an initial condition that they put on their model, which completely would change the outcome of their model if they changed that initial condition. So, uh, people, scientists, every scientist should take any result, any model, any data, even with a grain of salt and open-mindedly. So, back to what you were saying, it's very tough socially to say something like, I don't know if we're 100, we should be 100% certain about if the Big Bang happened, like everyone's saying it happened. And it's very tough socially because you were saying people have this certain tone when you start asking those questions, right? That it's just hard on people who not even disagree but just question it. That's all they're doing.
And that's kind of what I've been experiencing some as
Mm-hmm.
I'm interacting and talking to more astrophysicists and plasma physicists and particle physicists, and you know talk about, you can say the same thing about gravitational waves. Like, I'm not sure if we're measuring gravitational waves. I'm not sure.
Mm-hmm.
You're trying to measure something that is 1/10,000th or 100,000th the width of a hydrogen atom.
Mm-hmm.
I'm not sure we can measure that.
Yeah.
And then you're measuring it with lasers in a vacuum thing that's been vacuum pumped down to tenfold less ions in it than what are in space, and yet the light can still move through it. Well, what's it moving through?
Mm-hmm.
If you've taken out everything, what's it moving through? And
Mm-hmm.
then this brings you back to the ether, and then you can drive people mad, right?
Yeah, I was gonna say that's a slippery slope there. Yeah.
but true,
Yeah,
right?
yeah, yeah. It's
Because
yeah.
that's how the experiments performed.
Mm-hmm.
So, you know, I just appreciate your freshness and your take on, you know, what you're doing. I really appreciate the work you've done. It was really
Thank you.
interesting. It was really interesting to me to see how, uh, because that was the one part I had forgot to mention that you brought up, was that you did measure. Uh, there's at least one event that was very strong where you saw movement in the opposite direction,
Mm-hmm.
and it's in crystal clear, like unequivocally
Yes.
going in the quote unquote wrong direction.
Right.
And it's like, it was so cool to see the breakdown, and how you made it hard even for yourself to say that a KHI even happened, because you didn't allow for heavy ions to be used, because you wanted to pad your result so that the incorporation of heavy atoms wouldn't cause you to have, I guess, what some other people are calling false positive
Right.
KHI events. Like,
Right.
I guess maybe so. How much would it have differed your data, just ballpark, had you included the heavy ion event, or the heavy ion stream?
So we observed KHI to occur in about 40% of our events without the heavy ions. I would guesstimate that it would have increased that to about 70, 80% being KHI positive. Yeah.
So do you think that so you're saying, do you think that it's actually then much more towards a 70-80%, or do you think that it's this maybe less, around half the time you get these KHI events, KHI waves?
Oh man. I think that it definitely should be occurring more often. I tried to take the most conservative approach because of what some scientists would like. I tried to get these scientists that would disagree completely that KHI is happening to at least say, hey, look, we took the most conservative approach and it's still satisfying these conditions. That's why I did that, so that any scientist could get on board with
I kind
that.
of figured that. I've kind of it,
Okay.
it, it,
Yeah.
it actually wouldn't have surprised me if you submitted the paper with it and the reviewer said take it out because I don't believe it, and only if you take it out and you still observe it will I believe it.
Right. So I that's actually not what happened. I was just pre-planning that that might happen. I was like, okay, this if this happens, like I'm just gonna, nip it in the bud here.
Well, so I'm of the same mindset. There were many experiments even that end up in the paper in supplemental figures
Yeah.
where before you submit the paper, you're like, what are they going to ask for?
Hmm.
Because, and then you always leave them a convenient thing to ask for that you already did too. You just didn't put it in there.
Yeah, right. Exactly. Yeah. No, my reviewers actually were on the other side of the spectrum. They fully believed that KHI was occurring, and they actually wanted me to put in that a different approach that KHI was happening could happen in up to 97% of events uh, that we observed, based on this sort of it's called the wave vector direction essentially, and look at all the different directions it could take, and if it's possible that one of these directions could satisfy the KHI condition, then count it as satisfied. That's what they wanted.
But that's not cool either.
I
Because now
know, I know.
now you're setting the deck the other way.
Right, right.
Yeah, I mean, and this is what we have to deal with though.
Yep.
When you're in the field, this is what you have to deal with, and you have all of these egos flying around, and you have to, if you want your paper published, you have to satisfy them. And sometimes I wouldn't say it's difficult to hold your integrity, but sometimes it's frustrating.
Hmm.
You know, it
That's a
can
good
be
way to put
frustrating.
it, because it's not like it's not like I had to change my entire paper or anything like that. Um, I just had to essentially do that extra bit of analysis and put a couple of figures into supplemental information and call it good. And they were satisfied. I was satisfied. The 99% of my paper was the same, so it was still fine. But yeah, it can be frustrating.
So this is the last question I want to ask you
Okay.
because I've taken so much of your time and I do appreciate it. But, and you're not that old. However, you know, you're in the graduate school phase. So, what would you say to people in high school right now or early undergrad about getting into science at all, getting into physics? Like, what would what would be your advice if somebody gets bit by the bug and they say, you know what, I gotta go try this.
I
What would you?
think, yeah, I think that the first thing I would say is make sure you're truly interested in it. And secondly, if you are truly interested in it, then don't give up on that, right? You just keep, you cannot give up on that. Don't be discouraged. Because like we said at the very beginning of this whole podcast, it's going to be, on a good day, 90% failure, 10% successes. Uh, and then if you get past that part of, okay, never be discouraged, accept that I'm going to fail many more times than I succeed. Uh, all that's left to do from there is just be able to put in the work and the time, and I think you're going to have not only a successful scientific career, but a fun one, which and a memorable learning experience throughout it. So that's my advice to these younger scientists, I should say,
Yeah,
in
because
high
you're still
school.
pretty young, bud.
Yeah, I still have a lot to learn as well, and that should be something that every scientist takes too. You always have more to learn. You're never at the end of the road with that.
I'm 52, and trust me, I still feel like a blithering idiot most of the time
Yeah,
because there's
me
so
too.
much to know and so much to learn. And I mean, I have a unique story that'll probably get out there at some point, but uh, I kind of took a 10-year break, and over a decade, all I did was the research that I wanted to do.
Hmm.
Taught myself to program in C++ and did all kinds of stuff that I never thought in a million years I would have the opportunity to look into or even just learn about.
Hmm.
Like for me, plasma cosmology and cosmology and all of this stuff, like astrophysics in general, it was just, it's so cool.
It is so
So
cool.
cool. And I had learned enough physics through information theory and doing large data set analysis, and I realized that I had already used a lot of the statistical methods that are used in astrophysics, and I'm like, oh well, I have a tiny little foothold here where I can start teaching myself and already have a kind of a deeper understanding of the analysis methods. And
Yeah.
from there, it was just like a fish to water and read everything I possibly could and
Hmm.
came to the realization that we really don't know anything. We really don't know anything.
Yeah. We
But
really
we know
don't.
so much, but we don't know anything, but we know so much.
Hmm. Yeah.
And it's clear because of people like you, the young fellows like you that are really doing great work and putting it out there. I appreciate your time today and good luck in your future endeavors.
Thank you. I appreciate this entire conversation. Thanks for having me. Yeah.
Well, maybe we'll have to do it again when your next paper comes out.
Yeah, that'd be great. That'd
All
be
right,
great.
would love to.
Yeah.
All right, Jake. Well, thank you so much. You take care.
You too.